Thank you. So I just started recording. So now we have now it's recorded. And first of all, welcome everybody. So as Clara already mentioned, I'm Christian. It's a pleasure for me that we are today. To me and Aarti, she will introduce herself after me. It's a pleasure for us that we are having this kind of format with you in this World Academy, and I'm very excited. Maybe a bit background to myself. I had the luxury during the first academy years that I was not only a colleague of them and a kind of mentor. I was also living with all the academy people in the same house over the whole period where they were here in Stuttgart. So I was very excited, like learning a lot from very different countries, very different cultures, and also innocent. We spent some time here. So I'm very happy that it happens and that we have the opportunity to talk to you and to give you some of our understandings. And I'm very happy and thankful if also we are getting from you some comments, feedbacks, also questions later on, because I think it's very important that we are interested also to learn from you. And in this way, Aarti, she will start the initial slides and the presentation. I will take over, and but we both will guide you and show you some information in our presentation today. Yeah, Aarti.
Hi everyone, I'm Aarti.
So, okay.
Great. So you are all also welcome to switch on your cameras if you like to share your faces with us. If you have the bandwidth, but I would request everyone to just stay on mute so that we don't have any disturbances. If anybody wants to raise a question, please feel free to just raise your hand because this is Zoom, and we can then take any questions that you like.
So let's start sharing. Okay.
Perfect. Great. So maybe we begin with just a little bit background of ourselves. I'm Aarti Dhingra. I'm an architect by training. I came to Transsolar about 9 months ago. And before this, I was working in India as an architect. So I was working primarily in temperate and subtropical regions of India, which was predominantly the foothills of the Himalayas. And I was working there on site, in construction sites, working hands-on with building materials and understanding different realities of different climates and how to respond to those climates. And then I came to Germany to do my master's in integrated urbanism and sustainable design. And after that, I started working with Transsolar, which has been a wonderful experience. And Christian can now introduce himself.
No, and I forgot to mention, besides the academy, I'm an engineer from background, mechanical engineer, not really in building physics, but I was always very excited about efficient buildings and also about architecture, about the kind of performance of architecture in combination with technical solutions. And I really was interested in how can I, as an engineer, how can I support and guide architecture to become more efficient, let's say, in the end of the day. Okay.
Great. Moving on. Okay. So for today's lecture, the idea is to understand the different factors and elements that make up different climates. And by the end of this lecture, we'll try to get you to an understanding that you will be able to understand the relationship of architecture to weather and climate, and be able to review different climate studies, what they mean, how they can help you design a building in its various forms and elements, and also to understand some climate generation, analysis generation tools that are available online, and also to get you excited about climate responsive design. So like I said, if you have any questions, just feel free to raise your hand or drop it in the chat, and then we will answer all the questions. So this is how we've divided the lecture today. We'll begin with an introduction, then we'll go on to understanding some factors that make up the climate, what are the different zones on the planet, and how we can respond to those different climate zones. Then Christian will take over to help explain the climate analysis and understand the different elements that go into a climate analysis. And then we'll also showcase an example project, or maybe 2 example projects, and then it's your turn. So let's begin. Are there any questions so far? Okay, let's begin. So what is the difference between climate and weather? Let's begin with understanding what is climate actually. So as we all know, the Earth revolves on its own, around the sun and on its own axis, rotates on its own axis, and it creates climate and weather patterns. So basically these are created by the sun's solar energy, which is interacting with the land and the water and the air on the Earth. And climate is a long-term pattern of weather in a particular area. And weather is a short-term changes that happen from minutes to minutes or months to months in the atmosphere. And so basically the average weather pattern defines the climate of a region. And we can go further. So there are very dynamic factors that influence the climate system, and it's comprised of the atmosphere, which is the air, the hydrosphere, which is all the water bodies, the seas, ocean, everything, the cryosphere, which is the ice, and the lithosphere, which is the ground, rocks, tectonic plates, and the biosphere, which is the ecosystem. So how the plants and the biodiversity is also affects the microclimates and climate of the region. To understand climates, we break it down into certain, sorry, there's a person in the waiting room, I will just admit them. So we break it down into certain measurable physiochemical values, which are solar radiation, air temperature, precipitation, evaporation, humidity, even the population, wind, and pressure. So when we understand these values, we are able to tell what a climate of a location is like. And then we are also dependent on certain geographical factors like the latitude, the land, whether it is close to the ocean, what is the altitude, whether it's a mountain area, whether it's a desert, whether it's a plain, and the exposure to other factors such as if it's an urban area or if it's a forested area and so on. So we'll take a little bit of look into all of this in detail. So based on latitude, as you all know, we divide the climate into tropical, subtropical, temperate, and polar zones based on the radiation. So for example, there is maximum solar radiation in the month of June, and then therefore that's the summer months, and because of the rotation, this is how the climate regions are formed. So the polar regions get less sun, and the regions which are closer to the equator, they get more sun. In addition to this, there is the constant exchange which is happening between the sea and the land. So there is the wind that is generated because the air, hot air rises up, which is heated on the land, and the cold air flows in from the water, and this creates wind movement patterns, which affects the climate. In addition to this, altitude affects the climate. So altitude decreases pressure, and it makes the air rare, and it increases wind. So it also affects the rain patterns of the area. So there are windward sides and leeward sides of the mountain which generate monsoon winds. And then there are other factors like whether it is an urban area. So for example, if everything is concretized in a city, it will generate a different kind of microclimate, which is known as an urban heat island. So what really generates the different climate zones? We can break it into majorly 3 parts. This is the global radiation that the Earth receives. On top of that, there is the precipitation, so the rainfall or snow, which the Earth receives. And then there is the atmospheric circulation, which is the wind. So when you overlap these 3 parts, we predominantly get these maps. This is the map of the solar radiation on the Earth. You can see that close to the equator, it receives most of the sun. As we go away from the equator, it's getting lesser and lesser, and towards the top and the bottom, which are the polar areas, it's much less. Then this is the total annual rainfall. Again, you can see that it's the region where the rainforests are found. These are predominantly in the areas which get a lot of rainfall and a lot of heat. Overlapping with that, there is our trade winds, which govern the rainfall, monsoon, and temperature flow of the entire globe, basically. So, for example, looking at the African continent, you can see how in a section the trade winds flow from the north to the south, and then where the warm air rises up, the cool air is always taking in to cover up that space. In addition to this, there are these deep ocean currents, which also circulate the temperature in the oceans and the seas. And the cold water and the warm water flow in a way that it also creates wind patterns. And this wind patterns then defines the coastal winds and so on. So what we have based on all these layers, when we overlap, we get a detailed climate classification, which is broadly classified in two ways. There are certain genetic classifications, which classify based on the causes of the climate. For example, where it is generated. These are like the Flown or the Neef classifications. But what we use commonly is the effective classification, which is based on what are the effects of the climate. So the most common one to use is the Köppen and Geiger, and this is the map of this one. So according to the Köppen-Geiger climate classification, there are around 30 zones of climate that are in the world, and they are these. So from tropical rainforest to arid deserts to cold, dry summer, hot summer, dry winter, cold summer, cold winter, dry summer, and going all the way to polar frost. So these are 30 different climate zones, and each of them create very different and very unique characteristics in every possible way. So let's take an example and let's look at a broad classification. So let's for a moment just remember that we have 30, but just for the sake of understanding, let's take 4 broad classifications, which are the polar zones, the temperate zones, the tropical and subtropical zones. So so when we overlay all these layers of solar radiation, precipitation, humidity, wind, atmospheric pressure, what we finally get is something that is a completely different geography, a different vegetation, soil, topography, and it looks something like this. You might be familiar looking at such environments in your area. And naturally, as these climates begin to change, the soil and vegetation changes. So as you know that in rainforests, there are broad-leaved species. And in temperate forests, there are deciduous, coniferous species, and so on, which naturally means that the kind of produce that is grown there, like the food we eat, for example, also changes. So in rainforests, you would find fruits like papaya, banana, pineapples, and so on. In subtropical areas, you would find oranges, figs, dates, and so on, which basically means that the food being consumed changes. So the culture, languages, everything is changing from these areas. And moving on. This also means that the natural resources that are available there, or the locally available materials that naturally are found there or grow there, are also changing. For example, in tropical areas, bamboo grows abundantly. And in most subtropical areas, you would find a lot of limestone or a lot of sandstone and so on. And in temperate areas, there is abundance of wood, especially coniferous trees like pine wood or cedar wood. And in polar areas, there's of course ice. So what this means is that predominantly in traditional buildings, people used to build with whatever was available to them in their immediate surroundings. And that's why you see buildings which are predominantly made of these materials, because they were right there. And also something that changes further is Naturally, the clothing. So our body's first response to adapt to the climate is to wear comfortable clothes, which give us adequate amount of ventilation, protection, and so on. So if you look at someone in a tropical area, that's the clothes they would wear. In a subtropical, they would cover their face, cover their head because it's too sunny. In a temperate area, they would cover their body with a warm coat, and in a polar area, even a thicker coat. So now it's time for your turn, and we want to ask you, how do you think architecture changes? And the hint is, if you look at the clothes, you'll be able to tell how the architecture changes. So maybe please raise your hands and let us know some answers.
Or some thoughts or of your kind of experience,
Yeah.
which you also have, just to, I think it's important that we're, talking about our general understanding. And I think innocent, I'm not sure if it was you or if it was some names coming again. But when you came here to Germany, it was winter time or even October time, there was a kind of hard change in clothing, I could imagine.
Yes, true.
Would anybody like to take a guess or take a shot at answering?
No, I think maybe if I add to it, the interesting is here, everybody, we have this all season kind of clothing. Where we are in winter, everybody's getting super insulated with a big jacket. And innocent, I remember a very, very huge jacket in your case, because coming from a very warm climate, it's like the expectation is also different, or the experience of what someone is used to before when season changes.
Mm-hmm.
Yeah, and here it's like in winter, it can really drop down to whatever, -10, and even extremes -20 degrees Celsius. And that means that we're really kind of wearing a big jacket and reacting in our clothing. And in summer, it even helps us that when temperature goes up to 35 degrees, we just wear short clothes, and in this way can manage to almost feel quite comfortable, despite very extreme days and hot days. But it's the way then we kind of react.
Mm-hmm. Exactly. So like Christian said, that in the summer, as you see on the picture in the left, the person needs a lot of ventilation. So naturally, the clothes that you would wear is light, airy, breathable. And in, let's say, in a subtropical area, the person you can see needs a lot of sun protection in the day, but also needs warmth in the night. That's why they're lighting a fire. And so they need something which is also protective, but also breathable in the summer, in the hot summer day, but also something that can be protective in the night. So for example, something warm in the night. And if you go to the third picture, the people need protection from the cold, and they need sun exposure, especially in the winter. So something which is heavy, insulating, but is also adaptable is very important. And then from the fourth picture, it's self-evident that it needs a lot of protection from the cold and heavier insulating material. But why are we suddenly talking about clothes? The idea is that architecture changes exactly like that. So when you build a building or when you design for a specific climate, it's as natural as you would put on your clothes for summer or put on your clothes for winter. The building is your next best shelter next to your clothes. So it's the next skin, is the third skin. And the first being your own skin, the second being your clothes, and the third being the building. So now so based on these principles, this is how we started building a couple of centuries ago, climate responsive design, and this is how we're going now. Everybody is just building the same, whether it's a tropical climate or whether it's a subtropical temperate climate. These are actually real houses from the same locations. And the question is, how do we go from here? If we are creating the same conditions to live inside and insulating ourselves completely from the outside, how do we do this better? How can we understand the climate and respond to it in a more conscious way? So the first step that we can begin with any project is to start with a site study, which basically means to understand the climate conditions of the site. So the components of this would be to understand the sun angle of your location, understand what is the solar radiation, if there is any immediate shading, if there are any tall buildings or trees around, understand the temperature, precipitation. So for example, if it's a rainy area or if it snows there or if it gets very relatively less rain, because this would mean how you design your architecture. If it's there is humidity in the atmosphere, what is the wind direction, what are the temperature differences, and so on. And then you would raise the question that how do you translate this to design? If you have any guesses, now is your second chance to to also present some thoughts.
Yeah, I think what would be really helpful, I think I hope that you are kind of understanding us, because I think it would be really great if, especially if there's a group here in the Zoom, because we're having now 6 or 7 Zoom members. It would be really great if we are getting a feedback from the group or people, so that we know that you hear us, because it would be a pity if we are missing all the people. And I think I would rather prefer than to have another time where we really present to all the group. So please give us a feedback if we are having all the people here. Yeah, and I think it would be also really great if you are maybe as a starting point, if you give us an idea, what is the typical, let's say, traditional architecture, a bit of some like high level experience from your perspective. What is traditional architecture looking like in your home country? And maybe also to give us an insight, what is the kind of modern way to deal with it? What are modern buildings looking like? Is it like glazed buildings? Is it fully conditioned buildings? And I think it would be really important for me now to to hear from you something, if the group is available, just for organization.
Let's see. Thanks, Christian, for that. I see Priscilla connected. Priscilla is the professor that is in the classroom with all the other students. So I will just ask directly here if she can hear us and if we are following the lecture.
Yeah, I think that would be great to know.
Yeah. Priscilla, can you hear us?
Or maybe write in the chat if talking is not working.
Okay, let me try. Or even Innocent, if you have any update, or the other students, if meanwhile you want to answer Christian's and Aarti questions, feel free to unmute yourself and speak loud.
Okay, just to answer your question, in terms of the traditional architecture that is available in Zimbabwe, basically that is the type of architecture that is seen in the countryside, like in the villages. So what is there, you have more of like rounder villas, like buildings built based on circles, and most of these, they're built out of, some of them out of mud and some of them out of bricks, but the bricks, some of them are bent, some of them are just simply molded out of the earth without any burning. Then in terms of the roofing material, we mainly use straw or thatch, that is grass, maybe to simplify it, as a roofing material. That is more of like the traditional type of architecture that you see in the villages. But now when you move into the urban areas, in towns, in cities, now you have these glasses type of modernist type of architecture with a lot of air conditioning units pasted on the walls, you know, informing the type of architecture that you would see around. But the most material now concrete, and then you also have maybe roofing from tiles and metal sheets.
Right. Okay, thank you, Innocent, for that answer. That shows us, okay, someone is listening. But I request Teresa, Precision, and Faith, and also Priscilla to just give us a heads up, maybe just raise your hand or just allow us to know that you can hear us fine and you're there. Are you there?
I wrote also in the chat, but no answer so far. Innocent, would you mind to give her a very quick call?
Yeah,
Oh,
I think.
Okay, let me do that.
Yeah, I understand this would be great. And if it's today not really working, then let's rather find another possible time, because I think it would be good to have all this attending, or also to have an exchange. I think that would be really appreciated for us. Thank you.
Yeah, I think Priscilla had her connection dropping.
Okay. But they are still connected.
She's saying,
Okay.
she said she's now trying to reconnect.
Okay.
Okay.
Yeah.
Let's wait quickly so that we.
And the other people, are you Teresa, Precision, Faith?
Ah, we see somebody.
Hi, Benaya. Nice to see you. Hi guys, so who all are here now? Are we more people now?
Maybe just raise your hands if you can hear us well. If we have, if we see raised hands, we will try it, or we will go on, or we try to go on.
So Sylvester, Faith, Precision. Okay, Precision is here.
Yeah, super.
Yeah, great. I see also some webcam.
Yeah,
Sylvester.
Priscilla, she says we can proceed. They are connected using the one written Faith.
Okay,
Okay, super.
great,
Perfect.
great.
Great. Thanks, Innocent, and thanks, Christian and Aarti. Then I guess we can proceed.
Perfect. Thank you, Clara. Okay, so I hope the previous part which was missed was not really, I don't know.
It's recorded anyway.
Yeah.
I think that is
Okay.
fine.
Okay, great. So let's begin with understanding how you will approach a project when you get as an architect or as a student a building site. What are the things that can help you decide how to design with respect to climate? And the first thing would be to understand the sun. And so there would be the solar radiation, there would be the sun angle, and there would be the temperature. And then the next thing would be to understand rainfall patterns. So naturally, if you look at places which get more rainfall, they have sloping roofs. Places which get less rainfall, they have more flat roofs, and so on. So also depending on the quantity of rainfall you get in a time, decides the angle of the roof. And then humidity, what can you decide by humidity? So these are some things that we will go into detail, and we would like to also invite you to give us some feedback if you think there is some impact of humidity on the buildings that you live in, or some impact of the wind. Please feel free to raise your hand, and we'll be happy to incorporate your feedback. So yes, is someone saying something? Okay. So to give you an example, here are the sun paths of 4 different places in the world. And I believe in the previous lectures, you were already introduced to the concept of the sun path. So if you look at Oslo, and let's say you look at the one on the right, which is Cape Town, in Oslo, the sun is coming largely vertically from the east and west. And from Cape Town, it's coming from the north. And in Kinshasa, it's coming also from the top. So what does this mean for a building? Imagine you were standing in this kind of sun, you would automatically raise your hand and protect your eyes, right? So if it's coming vertically, you would need vertical protectors. If it's coming horizontally, you would put your hands horizontally over your eyes. So the building works in the same way. In certain places, when the sun is coming from the top, you need horizontal protection from the windows. And if it's coming from the front, you need vertical protection. So this is how a site study works. And all these inputs can help you in these ways to design with respect to climate. So the sun angle will decide what is your building orientation, where are your larger facades facing. The solar radiation will decide how much window sizes you want to give on which facade of the building. And the precipitation would decide your roof angles and how you channelize water on the roofs of the building. And then humidity would help you decide the breathability of materials, whether you want to allow humidity or whether you want to really ventilate it, and so on. And then wind would also help you decide the protection, to where to put wind protection, and so on. And then the day and night temperature differences would help you decide whether you want to utilize those differences with respect to thermal mass, to understand that the day, if it's warmer in the day and colder in the night, maybe you want to store the heat of the day to use to cool the night. And of course, if there is a local mountain or a lake or a water body, your site would again respond to these conditions. And if there are trees, they could act as shading and wind buffers. And if there is cloud, if it's a very cloudy place, this would also decide how much daylight you get into your space and the window sizes and so on. So now I give it over to Christian, who will take you into detail of all these elements and how you can analyze them.
Yeah, I think it's in general, yeah, I think there is a kind of macrosphere, and then there's a micro whatever space, let's say, where we say also we have the kind of the microclimate. Microclimate is something which is very locally. We are really, it's really relevant for us as also climate engineers to dig into specific site conditions. And specific site conditions, some are more varying, some are less varying, if you're like whatever 10, 20, 30 kilometers away. But what is really relevant is that we are digging into the boundary conditions, like what are air temperature ranges, what are the air humidity ranges, what is the solar radiation. Solar radiation is not so fluctuating if you're going whatever 50 to 100 kilometers forward. But wind is something very site specific also. If you have mountains next to it, if you have the seaside next to the location, and also and what is also very kind of more robust is the soil condition. It's really relevant for us. What is the soil property condition? Is there water, running through somehow, or is it containing a lot of water? And that helps us then to give us some kind of understanding. How could architecture also passively, first place passively, then actively, and so on, be designed in order to become, let's say, in itself robust and efficient? So the part, we just highlight here now some, let's say, key elements which we are really interested, even before we talk about architecture. For us, it's relevant to get an understanding of, what is the boundary conditions, as I mentioned before, and that's temperature in one place, if it's in degrees Celsius, in Fahrenheit, or in Kelvin, whatever. For us, interesting is to get an understanding and a sense of the air temperature, outdoor air temperature, not at a certain point in time. It's important for a kind of over a longer period to know how is air temperature changing, how is it varying during daytimes, during day and night time, and then also to get based out of this in relation with humidity and cloudiness to get an understanding of sky temperature influences. And ground temperature and dew point temperature and so on. I will get to this later in more detail, what is behind it. Because the question is for us, when we know how temperature is changing, what is the kind of increase during the day, during short time periods, this will tell us a bit more about what strategies might be really efficient and might be really worth considering in the, let's say, passive cooling strategies and so on. For us, it's like climate engineers, okay, we relate to given data, which is in the first place, which is measured all over the world, which is then distributed for energy calculations. But we also are very interested if there is locally more, let's say, actual data from the past year, for example, or the past 2 years, so that we are generating also kind of an overlay, because we realized that in the past years and decades, temperatures were really significantly changing, and also very depending to if it's in a city, or where it's in a city located. If it's a part of the city which is ventilated well from outside, and that is something which in a site study is very important for us. So here you see an example of air temperature throughout a year, which was from measured data, which is used for energy calculations. And what you see here is, let me just take the pointer. Where is it? Here. So the laser pointer. And what you see here, this is for Dubai, a whole year. A whole year means from January 1st to December 31st. And what you see is the dry bulb temperature, so the air temperature outside, which kind of goes in winter down to this 12 degrees Celsius, but also in summer goes up to 40, 47, 46, 47 degrees Celsius. And this chart, what we are interested always in is what is the extremes, like what is the cold, what is the hot side, but also what is the kind of band we see here. So you see in summer, for example, it goes from 47, it goes down to roughly 32 degrees Celsius or 30 around. And that gives us a kind of initial idea, you know, when the summer temperature varies between 30 to 46 degrees Celsius, you know, is there really a potential when we think about our expectation for the interior climate? You know, I think everybody of us, we have a kind of expectation. What is the interior temperature in a space? And that is, for example, in Germany, we would say we would like to stay between 20 and whatever 30 degrees. So if we apply our expectation, we overlay it with the given boundary conditions in Dubai, then let me just sketch here quickly. Then we can see that when we integrate our expectation here from 20 to 30 degrees Celsius, yeah, and the coloring is not so reasonable, but we would like to be in this range, which I'm just indicating. So we have the situation that in summer we cannot really drop that down to get into the range, yeah, because what we as humans do, we produce heat anyway. We have sun which produces heat, and so we have a lot of heat which anyway is other than the air temperature there. We would really need to think about how can we efficiently cool down from that range to get into our expected comfort range. On the other hand, during the winter time, so what you see on the left side down here, yeah, that is kind of temperatures which are not so far away below our 20 degrees Celsius. So to raise like these, whatever, 12 to 20 degrees Celsius, yeah, we would need to think about where do we get the power, the force from? And we have all the heat that people produce, we have all the heat that comes from sun. Yeah, so I would, in the first place, I would really say, okay, do we really need heating at all actively? Or isn't it the possibility to say, couldn't we capture heat anyway during daytime from sun and integrate it into our conceptual idea and to say, what would we need to do in order to make the most out of this available natural source of heat in winter in order that we're really avoiding and not having heating at all. So this is just a kind of, way of thinking which I would like to raise. I think we sometimes, we make it too complicated. Yeah, we say, okay, what is what we don't really look at the pure boundary conditions. And sometimes we make it too complicated and we talk to clients which say, I need a fully conditioned space. Yeah, and then this means you need heating, you need cooling. We come from the wrong direction from my point of view. And I think it's like, first of all, we should raise the question, what is the boundary condition, what is given? And then we should say, no, maybe we don't need heating at all. We just talk about cooling, for example, and get rid of kind of, in the first place, of all this overloading, and go on from there. So jumping to the next picture, the last picture was a sequence. We call this here a kind of a temperature sequence throughout the whole year. I forgot to mention the upper chart here. The upper chart is a so-called heat map diagram, and you see the same kind of the whole year from January to the end of December, and you see the daily hours on the left from 0 to 24. So every vertical line here or element is a day of the year. And every dot is representing also kind of an hour. And what you now see here is that from 0 to 8 o'clock or 6 o'clock, you see here, these are morning hours from 18 to 24. These are the very late evening hours. And you see a kind of statistic already, which indicates that below 19 degrees, between 19 to 26 degrees, and it gives you a kind of percentage where the temperature throughout the year is in that range. And what we see is that, for example, between 19 to 23 degrees Celsius, temperatures are even here for more than 50% of time. Yeah? And that is interesting. So I would say if the temperatures exterior in that range, then we could have almost 50% of time of the year, we could have the potential to passively, to maximize the natural power and forces we have in order to really condition, or not to condition, to have a very interesting and very comfortable interior space. And I think if you tell that to someone in Dubai, they would start screaming. And they would say, if someone comes and says to me, 50% of time of the year, you can reach with quite comfortable conditions with passive measures. Yeah, and I think just keep it in mind. I mean, it's not so, let's say, far off the way. Yeah, I mean, the potential are there. It's just like that our systems, yeah, they are already kind of oversized and they're running whole years, so that you're not using this potential. We're just saying, no, we're kind of scared or whatever, or architecture cannot react on it, or we build a fully glazed building in Dubai, which is kind of the wrong message in most cases. So, and I think this is just to give you an idea how we are kind of approaching it. Okay, so this is again statistics. So for us, interesting is what is the, you know, how often is our temperature, for example, in between 30 and or 20 and 32 degrees. So, but it's again similar like what I've explained before. What interests us is these ranges of temperature, so that we can identify, can we really operate the building in natural mode only, and what is the potential time frame? Because what we are now learning extremely in Germany also is that energy is something very limited, and we have, and it's weird that we are learning it now this way, but I mean, we know that temperature is that energy is something limited, which we are producing actively in order to compensate and to have energy. But now we are learning that, okay, due to boundary conditions, politics, we are learning, okay, we need to really think about how can we minimize energy consumption, and that means go back to natural processes. So that's just an indication again. So here we were a bit more critical, or in this kind of study where we said you have a cooler side in winter, where you need to think about how can you maximize the passive heating. You have a itself directly comfortable range, which is highlighted green. So in this range, you could directly stick outside, which is also already a lot of time. And then you have potential times when you considering more conventional climatic conditions inside up to 26 degrees Celsius, you would have the red side, which is more or less active cooling. But this is really like intending that you are following more conventional conditioning solutions. And I think our intent would always be to extend that the comfort range is not 26 degrees in upper part, that we would really like to develop solutions and ideas which also feel more comfortable if you go up to 28 to 30 degrees Celsius. We come later to it, and this further stuff regarding this. So sky temperature, and I think in Dubai, especially in climates where you have a lot of sun, where you have very low amount of clouds, there is the sky temperature, which during nighttime is even generating situations where you really freeze, and where you really have a problem even. It's, you know, if you go to the desert or to the then you have a clear sky. It's the sand was very hot and warm during daytime, but during nighttime it really drops significantly down, because the sky itself is having a very cold temperature, and we have this called long wave radiation effect, so that cold surfaces are radiating cool, let's say, power on our human body and also on the environment. And that is even having a significant impact. If the sky is very cold, it goes down to really, the temperatures drop down very low, so that you need even to wear a kind of a suit, or you need to have a blanket on top of you or something, a carpet on top of you, so that you cover your body in order to avoid that freezing or feeling very cold happens. So measuring sky temperature, you see a bit the impact in the upper illustration, that the left one shows a clear sky temperature measured like with 34 degrees. Is it Celsius or Fahrenheit? Fahrenheit, I think, is shown here. And on the other hand, on the right, if the cloud is in front of the measuring device, you see that already 30 degrees difference in Fahrenheit. Which indicates that a cloud itself is flying in an intermediate height compared to the sky itself, so that it is already warmer. The level where the cloud is in with the sun and so on and everything is already a kind of a shell or an element which protects let's say if we are on the ground standing, which protects us from the very cold sky temperature. But we see a big potential if we are using sky with its very cold temperature as a kind of cooling source, and not only and also for architecture. So if you have night times where a lot of architecture is visible or seeing the sky, you have passages or you have corridors, or you have in master plans, for example, you would allow to open up and to see more of the sky, then the exterior environment would cool further down. Yeah, that this is a big kind of a potential. You know, what we do is we install, for example, shading solutions which are static. Yeah, and then they are blocking passages, corridors during night and daytime. But the ideal case would be that they are blocking it during daytime, but during nighttime they would open up. Yeah. And not only the architecture itself and the master planning and so on could profit from this, it's also that the lunar collector, like active systems, like for example, you know, solar thermal collectors during daytime taking the heat out of the sun in order to produce hot water. But in the same way, we have collectors with water pipes running in the back, which could even allow us during nighttime to exchange long wave radiation to the sky and then really produce cold water in a way. Yeah, something like when you would be in the desert during night, you would really feel the cold. This is the same principle as lunar collector. During nighttime, we really actively produce cold water, which could become part of a cooling solution, for example, in the buildings. So, I mean, but temperature, air temperature, and let's say sky temperature is one part of temperatures we are often talking about. What is for us very important is also the humidity in the air. So relative humidity. I know, I guess you now have rain season in Zimbabwe or in your region, but the humidity which is in the air is also having a significant impact on how do we sense comfort and what are also potential usages of water and air and so on. And what you see in this graph here is in a zoom in. Now we have just a week in May and June, or no, it's just a week. But what you see here in the red curve was the outdoor air temperature, which is available in this weather data from Dubai. And you see here that it drops from, or it goes from 30 to 40 degrees Celsius. Yeah, and what is quite interesting is in brown, the middle curve is the wet bulb temperature. Wet bulb temperature is, for example, when you have a fog machine or something which sprays water, yeah, with very fine elements. We sometimes have this in supermarkets when you have vegetables and you have, in order that they are not getting old and whatever. We have that the fog is sprayed on the vegetables, and this fog generates a cooling effect, which you can see here by the difference. Oh, sorry. Sorry. Yeah, you see the difference between the upper curve and the brown curve, and this effect it's from 42 or 41 degrees Celsius to almost 20 degrees Celsius. Like, that's crazy. It's 20 degrees. So 20 degrees temperature change, sensation of temperature would happen if you are spraying water, if you are doing fog instead of having the very dry outdoor air. If you spray water to it, then temperature is decreased by 20 degrees Celsius. And I mean, this is enormous. Yeah, for sure you have then high humidity level, but I mean, this is the main, or I think the main problem which we have here in Germany is if you have really dry days, when if you have very dry days, when outdoor humidity is really low and you have hot temperatures and you feel really then we are really like having an issue with comfort. So if you would really have water as a kind of cooling source, then it drops down temperature significantly. And that is, I mean, the weird in Dubai for sure is they have no water to use really on site. They have no, let's say, sweet water. They would need to produce it from salt water in order to use it. And that's also, again, energy consuming, yeah, for sure. But I think just for you to keep in mind that the principle and the effect of water to humidify water can have a really significant influence in certain times of the year. Yeah. And then the other thing which we have here is the dew point temperature, which is the lowest green, let's say, curve, which indicates if, let's say, like if we have a cold surface which is running at, for example, 18 degrees Celsius, yeah, then you would already, if dew point temperature is below that, then we would get condensation. And that is an issue when you install in some climates, you install these metal ceiling panels for cooling of spaces. Then it happens if it's very, very humid outside. Yeah, you bring in this air into a space, then it would happen that on the cold surface, water droplets would happen, and it could start that water drops down from the ceiling. Yeah, just by the air which enters a space, which flows by a cold surface, then it will happen that this that humidity drops down. So, and this is an example here, which a project I was working on in Muscat in Oman. It was an eco house. It's the intention was it's a building from a university which is kind of or which is more or less autark from energy, which means that all energy is produced on site, and all the conditioning, cooling, and heating and ventilation the energy is provided by the building itself. And they had these ceiling panels. I think in the end, it were metal ceiling panels, or even like with capillary systems. And what you see here is that on the right side, they operated with too cold temperatures. I think they started even with 12 degrees Celsius to operate the ceiling. And then for sure, I mean, it will happen that water drops out. And you see how on the right side, the water is kind of changing the color of the surface. And I think this is something we can avoid if we really are more following up on the, let's say, this topic of how cold is the surface, what is the air condition, and then we can avoid to have this kind of effects by running systems at a too low temperature also. I mean, I mentioned it before, the wet bulb temperature. You see an example here on the left. It's from the expo in Milano. It was the Austrian pavilion, which we supported, Breathing Austria. And what you see here is that really a huge impact, even in this climate of Milano, which is getting quite warm. We showed them this experience that when people are walking by these fog elements, which are producing, we call it dry mist nozzles and systems, they are producing very, very fine water drops, which even as I wear glasses, even if I'm standing a meter in front of it, I'm not getting water droplets on my glasses. And that's because due to the fine elements itself, they are kind of very fast mixing up with the air itself. So that I'm not even getting this effect on my glasses if I'm standing in front of it, that I really like rain, if rain falls on them, I'm not getting this effect. And this is quite, it's quite a simple, let's say, it's not so simple anymore because there's already a lot of technologies in order to, you know, to have the fresh water and to have a pressure in order to really generate these fine water droplets. But I mean, there are even simpler solutions, I guess you all know from even your homes. When you're sitting outside in a restaurant or in a cafe, sometimes there are these systems which are evaporating the air. And this is a similar principle. But there are details where you could even do it better, let's say, than conventional solutions. Okay, so the solar, I mean, we discussed about the cloud. I showed you the measurement of the cloud, and the cloud is somehow in between layer, and so that the sun, when it strikes the cloud, there's a lot reflected, but there's also some parts transmitted and absorbed. So, and I think this is just important to keep in mind. We have the high intense sun, which has really a high intensity with up to 1,300, whatever, 65 watts per square meter of extraterrestrial power, which means which arrives on the outer shell of the Earth. But then when it goes through the atmosphere, it is reduced, and typically we are ending up at whatever 1,000 watts per square meter. Yeah, when it passes through all the boundary layers, then some parts will be reflected again from the Earth to the sky, but then we are kind of this greenhouse effect, so that we have sun which comes in, but it will stay from its energy, it will stay in our more, let's say, direct environment. And the Earth itself is kind of emitting heat again by temperature differences to the sky and so on. But these are the main, let's say, forces. So the solar radiation, shortwave radiation, we call it. We have the long wave radiation, which is happening in between our ground temperature and also the sky temperature. And we have these potentials in order to consider in our, let's say, in architecture, in our climate responsive designs. Okay, so the solar radiation, I mean, it's a lot about energy and power. But what we need to keep in mind also is just a little simple example. If you have a hairdryer at home, they typically have in the range of 1,000 watts to whatever 2,000 watts of electrical power consumption. The sun itself has almost, on a clear day, if the sun is shining, you have almost the similar power as a hairdryer. With 1,000 watts, you have the same power on a square meter of footprint. And this is a lot of power. Imagine you're standing in the rest or bathroom and you keep the hairdryer on for whatever, 10 minutes or 15 minutes or 20 minutes. The space will heat enormous. So that's the same power which you have on a square meter on a sunny day. It's really worth to think about how could this be integrated and actively be used in architecture and also in technical systems. And there are really different ways to measure. We have the direct sun, which is when you see the sun, when you have a shading effects outside. This is, we call it the beam radiation, the direct radiation. We have, besides direct radiation, we have diffuse radiation, and diffuse radiation is if you are not seeing directly the sun, but you are getting reflections from the sky, you're getting from neighboring buildings. And these reflections can also have a significant impact on the comfort and on, let's say, the heat load, which is happening. Especially when you are thinking about glazed buildings. And on these highly glazed buildings, you have the reflection from the glass facades. This power can even be enormous and drive your whatever cooling demands standing next to a fully glazed building. I mean, there are, if you look in the web, you will find pictures about melting cars. The coloring of the cars is melting from a neighboring glazed building. In London, there is a good example. Or let's say a bad example in this case. And it is important if you are measuring it. There are these systems which are allowing to differentiate between direct radiation, diffuse radiation, and so on. It's just an example. And for example, here in this, I did not show here, but I think it's a more German climate with roughly 1,093 kilowatt hours per square meter and year. And what you see here is the monthly solar radiation or solar, let's say, insolation, which varies from blue. Blue is kind of the diffuse part, and red is the direct part. So the red is then when you see a shade of the sun, and the blue is just that the radiation is coming from more or less all sides. And you see that here in this climate, there is even almost similar amount of diffuse and direct radiation on a sunny day for a horizontal surface. So I think it's really important to understand if the climate is more driven by diffuse radiation, so even that you have a more cloudy sky, or if it's driven by more direct sun when you see the sun most of the time of the year, and you see the impacts on a different climatic situation. So that the direct part is increasing even throughout the month, throughout the, let's say, month from April to September. And then the direct part becomes more significant, almost double than the diffuse part. So it's important to understand these climatic conditions. And here we have an example from Canada, from Winnipeg. And Winnipeg is very interesting also from the climate. It has super cold winter conditions and it has warm summer conditions, but it has almost all year, you see here the solar radiation potential, it has almost the whole year, it has kind of comparable monthly solar radiation, which is shown here in kilowatt hours per square meter in month. So even if it's extremely cold and gets warm in summer, it has a very high temperature change from -40 to up to plus, let's say, 30 or 40 degrees Celsius, which is really extreme throughout the whole year. It allows to, use sun as a kind of energy source even in the cold winter seasons. Okay, and I jump over. I think I already struck a lot of this stuff. Oh, wrong direction. And just to mention here, we don't need to dig too much into it, but according to the sun path, how the sun is going around the buildings and the site, there might be really also significant differences in the facade orientations. For example, you see northern facade here in Winnipeg is getting very low amount of solar radiation. But then if you go to the south facade, it has almost the whole year kind of an equal solar exposure. But if you go to east and to west, yeah, you see that it's seasonal. So bringing it further, you could look at also statistically, that's again another way of looking at it. Here you see the solar radiation from the intensity, from how many watts per square meter, so what is the force in the actual point in time. You see again in a heat map diagram so that you could analyze, you know, when is on which facade, which time of the day you have a strong intensity. And what you see here is that the north facade is almost the whole time below 500 watts per square meter. And the rest, and there's almost no time when it's above 500 watts per square meter. So on the north facade, we don't have the hairdryer effect. So that it's so much power, but still we have a lot of times when it's between 100 and 500 watts per square meter. And it should just indicate when you go to a climate, look at what is the influence of sun on different facades. Look at it, and we will show some examples later on, which are kind of more related to your location. But if you see, for example, in a more let's say sun path where we are located here in Germany, then you have a very low sun angle in winter, which is indicated here on the left side by the red indicated, let's say, positioning of the sun, and you have the blue, which is then summer when the sun rises up to a very high level. And so you can really interact with the architecture based on the sun exposure. Okay, I jump over it. It's like it varies from location. It varies if we go to different locations. We have here indicated for high sun angles, June 21st, we have indicated Oslo, Rome, Vilma, Kinshasa, and Cape Town. And you see that the sun paths are extremely different. While in Vilma and Kinshasa, getting closer to the equator, you have quite high sun angles in mid of June. But in the other locations, like in Cape Town or even in Oslo, the sun path is even fairly lower, let's say. And it's coming also from different orientations, just to we should not forget that there is a north and a southern part where the sun comes during noontime from a different orientation. Okay, so then we have humidity as a topic. We have absolute humidity, which we can measure. We have relative humidity, which is then to consider how much humidity is relatively in the air available. And that is the kind of sensation when we talk about humidity in indoor environments, we always talk about relative humidity, because this is what we sense. We sense relative humidity if it's in a comfortable range. It varies, let's say comfortable ranges are defined between 20 and 65%. Yeah, that does not mean that above and below is uncomfortable, but it's a kind of intention to bring the relative humidity into this range. Okay? And it's strongly depending to the air temperature. So the higher the air temperature is, let's say, the lower the relative humidity while having the same, let's say, absolute humidity. Yeah? So if you change temperature, then your relative humidity is also influenced by it. Okay. So, and this brings us to a very important chart. It's a chart which we also are really showing often in projects, and it shows every dot is representing a point in time of the year, and you see the air temperature on the x-axis, so the outdoor temperature, and you see the absolute humidity on the y-axis, and every dot is a point in time of the year, which was from the measured weather data. And for us, it's quite interesting when we overlay kind of a conventional comfort range, which we are targeting. So here, for example, you see comfort by red indicated 20 degrees is the left line here, 26 degrees is the right line. And you see the kind of conventional relative humidity targets, which are indicated by the curves. So here's 30%, and here's 60 and 50%, and or 60 and 70%, and we try to be between 65% and 30%. So ideally, in our indoor environment, no, not ideally, I would say with conventional temperature and humidity targets, clients are often intending to be in the red surrounding, in the red curve here. So that means that all the dots we have, so all the points which are above the upper line here, this is typically a discussion in projects if we are kind of dehumidifying. So if we extract humidity out of the air in order to bring the relative humidity into the comfort range here. The dots which are on the right side, so from the right, yeah, we would need to cool them. Cooling means maybe, you know, fan coil solutions and stuff like this. Yeah, we apply those in order to bring down the temperature into the comfort range. And then for us here, it's like all the dots which are below, this would mean we bring humidity into it, and all the dots which are on the left side here, this would mean we have to heat up. Yeah, and I think this is why we like this chart, yeah, because you see by the amount of dots visually, you can see, is it humid? Is it too humid? Is it too hot? Is it too cold? Or is it too dry? And that is a kind of also a good starting point to start discussion and to say, how often is it above or how often is it below? And I mean, what you always also have to know is that systems, by definition, you know, they cannot bring 100% of solution. It's by definition it's not possible, because our human experience is what we define as comfort, means that, for example, 90% of people would feel comfortable under these boundary conditions. So even if you intend to have an ideal solution, it will never be ideal, because by definition, there will always be an amount of people which does not feel comfortable. So what I want to say with this is, don't try to overload your solutions. Yeah, find a good and appropriate solution which solves it for 90% and 95% of time, not 100%, because this is per definition not possible. Okay, then we have another topic, which is wind. Wind is very important for us for those kind of solutions, for architectural solutions, and also for master plans, for example. You see here some traditional ways of constructing where you have these kind of chimneys or wind catches, which allow to bring in or to extract air by the overflow. It's like I mean, in today's time, you build up Formula One cars with very aerodynamic solutions with spoilers. Yeah, and similar principles, and the spoiler presses down or presses down the car on the ground. I mean, you know, we are building up so many technologies and solutions which are for cars and for other stuff, which everybody likes to get a nice car in former times. And I hope in future it's not anymore in this way. Maybe have a more efficient bicycle or whatever. But, you know, honestly, in architecture, we had these principles. We used the forces of wind already in a very intelligent and clever way in the architecture. And you see here this kind of wind overflow element in the top of the building. And so the intention is that by the air that's flowing by, it generates an underpressure. So it takes out the air from the building below. And this is a force which is used in order to move the air even through a duct below the building. So it's a passive way of you know, replacing a fan. We don't need a fan while applying this kind of system. And it's just for sure architecturally it has a high impact because you have a chimney which is standing there and you need to solve all the airflow solutions in the architecture and not in the mechanical ducting. And that's why for us also, if we talk about efficient, let's say, architectural solutions, we also are interested in the wind situation. How much wind, from where does it come from? Is it coming from west, from north? Is it changing according to the season? Is it changing according to the time of the day? And these are all these kind of initial boundary conditions which we need to study. I jump over it because we are already kind of running late in time. And the similar things is for the, let's say, the property of the ground where we are building on. Yeah, so what we are interested in is what is the composition of it? Is it sand? Is it earth materials like, do we have clay there? Do we have water there? Because, I mean, what we do is with modern technical solutions, we just, you know, we build these chiller systems which have fan units. Yeah, and what we do is we dump the heat to the air. Yeah, and the air is a very fast reacting element itself. Yeah, so even if you breathe with your mouth, you feel hot air coming out of your human body if you're in an environment. So, and this is very fast reacting. I just take air in and I breathe it out, and then the air is warm. Yeah, so, and this is what we do with our technical solutions. Yeah, in the modern kind of approach, we dump just very fast the excess heat from our cooling process. We dump into the environment, and then we are wondering why we are generating microclimates which are super hot in summer. Yeah, I mean, we are instantaneously producing heat and we put it to the environment. And I mean, this was not the intention of intelligent architecture. Yeah, and also of solutions. And I mean, we have similar possibilities. We could dump the heat into the ground, and the ground is a more seasonal let's say, interaction. So when we dump it now into the ground, when it reacts with the environment, is a very slow process. Yeah? So we could really take this effect of, in summer, even overloading our environment with hot air. We could really generate a kind of a more smooth transition process until the air goes into, until from the ground it goes to the environment of the air. It's a much longer process. Yeah, so we could really use this kind of buffering effect. And this is why we are interested in the ground also for considering it in the, let's say, active and passive cooling strategies. And just to give you an example, even in, let's say, Dubai, we see that with the soil, which is has most gravel in it, we are in the ground at 8 degrees Celsius, 27 degrees Celsius. It's just if you go close to the surface of the ground, like here's 0 meters, or here's the top of the ground, and you go down 12 meters, for example. In the most upper layer, it's for sure fluctuating more according to the exterior conditions. But in the lower part of it, it's almost, you know, it converts like to a defined temperature, and that gives us a potential, you see, to annually to have a more, let's say, stabilized and robust source. But this requires that we are kind of going down into the ground and to use these potentials. And then let's say similar we had, for example, in Toronto, and there the average, let's say, condition is at 8 or 9 degrees Celsius. Yeah, so even if the exterior fluctuates between -40 and maybe plus 40 degrees Celsius, in the ground you have a very stabilized condition. Okay, I mean, for you, I think it's important that after our talk today, maybe you already did this for other stuff, there are web-based, but in the web there are is data available for weather. There are also tools available. We have, in the end of our presentation, we have a link to a tool which I find very interesting and nice to use in the first place if these questions come up for you. But we put here some sources and examples for you also to look at. Okay. One thing we just wanted to mention, when we use data for our energy modeling, often the database is the airport or some public available locations where you can get the data from, which is then treated by universities or whoever, or public institutions, in order to generate energy data for weather data for energy calculations. And important is that, as I mentioned also before, it can vary significantly from location to from the airport to the inner city. And you see an example here. The most upper part is weather data we took in from a climate source called Meteonorm. Yeah, and you see just look at the red dots, yeah, which is the hot part of it, the heat stress part. When we take the artificial generated one, when we go to the airport on site with a more actual data set from 2015, then you see that the red dots are significantly increasing. And when we then really go to measure data from site, again, it's significantly changing. So that means that, you know, if you have the possibility, really try to find weather data which is more related to the site and geographically, so more close to it, and also which is really maybe measured at a more actual time of year. So in order to really, you know, consider a kind of the change in climates, also microclimates and so on. Okay, I jump over data quality. We anyway sent this. You can see this again. Important is that the climatic data is consistent of the main drivers for us. It's temperature, air temperature, humidity, solar radiation, and also wind. And that we know even the wind direction ideally. So this is often not given. So look at the data very precise in the first place. Look at what is available. And if a data set is not, you know, providing you wind data and so on, then look for some other data. Just that you are in your evaluations, you're really considering the important drivers for your boundary conditions. There are some sources which you find online anyway. If you look for Energy Plus, for example, whether you find a big database which is already incorporating all of these sources like Energy Plus, IREC, TMY, typical meteorological years, and that you can use these as a starting point. Then again, as I mentioned before, look at, these climatic zones. Look at the psychrometric charts, and here's just a little example how we are kind of categorizing. If you look at your dots from your site, which you study, you could overlay this chart as a kind of mask in order to see, is it a more tropical, subtropical, temperate climate, or frost climate, and so to get an initial understanding also, and I think if you take this into consideration, you get a first idea is to which kind of region and solutions it would be also interesting to follow up on. So very important also is the effect, what affects human comfort. And I've showed this picture of humidity, of air, and so on. And I think what is important for us, it's the conventional definition of comfort. It's very different, what people are relating to comfort as a criteria. And there is an operative temperature, which is, for example, an ASHRAE taken into consideration. And the operative temperature is kind of an indicator which takes just air temperature and surface temperature of your environment. And it was derived based on kind of a standardized boundary conditions, what would be the human, which is in the space. And they have very defined criteria. And that is, for simplicity, for sure, they needed to follow this way. So they need to simplify. They need to say, okay, a human in an indoor environment wears whatever is the best in winter, and in summer, a bit less clothing. Yeah, and then that's it. But in reality, yeah, it's really significant, important, what you're doing as a human. Yeah? Are you standing? Are you sitting? Are you walking around or whatever? And this is why we say, we need to, good architecture looks, or let's say good solutions, not architecture only, but also technical solutions, look more holistic on the boundary conditions. So, what is the activity, humidity? What is the, we even talked about Ayurveda as a kind of, let's say, comfort element. Yeah, what is the coloring you see? Even color has an influence on your human body, on the blood flow and everything, the availability of daylight. Yeah, so I think it's important that, you can look at a much more holistic boundary condition than just looking at, for example, operative temperature, yeah, as a kind of indicator of comfort. And this is just what we would like to address with this chart. Yeah, we are really, we see a lot of potential in traditional ways of building, and if we modify them with the modern technologies, which we know, it's a modification, it's not a replacement of the principles. I think we could find very interesting and good solutions. Anyway, this is comfort, has so many aspects. How much our skin can evaporate, of losing heat and so on, of our temperature, of our blood flow, of what we are eating and so on. I learn also a lot from other cultures and discussions with colleagues. So just keep it in mind, there's so much more than just the temperature itself. And for the end, I have 2 examples. I take another 10 minutes, and then I hope we have a little bit more time also for your questions. But we are extending now a little bit because we started a bit late. But I would like to give you 2 examples. I jump over a little bit faster now, where we applied this discussion, these elements which we discussed previously about. And here's in Kampala, this is the Aga Khan Academy. And just to give you an idea about how can we, even based on the study of the outdoor conditions, how can you already give recommendations? And here in Kampala, if you look at temperature and the temperature change, you see it's just rarely going in the range of 30 degrees Celsius on the upper side and rarely going down to 15 degrees Celsius. So it has an enormous potential for a kind of natural ventilation. And also to think about how can this passively be used. So that's why we try to intensify the usage of night flushing, night and day flushing also if it's appropriate, so that we are kind of allowing for openings in order to cross-ventilate the interior of the space. If you look at temperature and humidity, then there is a kind of a challenge that the humidity is very high, but the temperature seems to be very, temperature is very good, but humidity is quite high. So if we are talking about space conditioning systems, we have to keep that in mind. We cannot just cool down a surface and then we get a condensation risk, for example. Then on the other hand, relative humidity, as I mentioned, is quite high. The rainfall, almost the whole year, there's some rain coming down. And there's also, then there's also kind of a change in relative humidity between day and night. And the good air change of the inside of the space is intending really to not to have humidity staying in the space. It's a kind of a movement we need to generate. We need also to flush out humidity of the interior of the space. Okay, so, but still, even if it's very humid in this climate, there's still a potential by humidification to even to further humidify the air, to reduce temperature. And I mean, it's here again, it's not so, temperature is really not bad. So I'm even wondering if we really need to humidify and to think further about this. Then the other topic is the shading. And if you look at the sun path being so close to the equator, The sun is coming from north and south side according to the season, and it's more or less just from east to west. It's going above the head, let's say, of the human, and then so we need to think about how can we maximize shading and effects by architecture and just apply movable shading parts where it's required. And this is here in this case, an example is that just by an overhang on the north facade, for example, which is purely like 30% from depth to height of a window, it already significantly reduces let's say, solar radiation on the window itself. And on the east facade, there is, let's say, there is a lower reduction, but you have the times of the year, more or less the whole time of the year, where you have sun striking the facade. Yeah? And on the north facade, you see that only in the gray part, which is remaining, is in the summer periods. Yeah? And then you would need to think about, okay, do I maybe extend it further in order to also reduce the solar radiation, which is then striking the window from that side. And so that means that for the windows and for the shading strategy, for north and south facades, overhangs are very efficient. And for east and west, due to the sun angles which come from lower directions in the morning and also in the evening, there would be anyway something movable maybe required, or something different as a kind of shading structure. Okay, so I jump over this now, and then the other topic for sure, like looking at such a climate, is topic of insulation, is a topic of facade properties, and I mean, you know this probably better than we, but there is, I mean, to insulate is not really the solution. Just you don't need to dump a lot of insulation material on the facades. It's more the question of how can you, protect from a lot of solar radiation and so on. And the roof itself, you can insulate it, but also on the other hand, you could also just lift it and build kind of a double layer solution, which we really, see often in, let's say, also in tropical climates also, that we are really trying to, or subtropical also, that we're really trying to take the heat out where it strikes the building. And that is the effect that we have here. So when the sun strikes the roof, so it comes here with 1000 whatever watts per square meter, then we are, by detaching here, by detaching direct contact from the lower part of the roof to the upper part, and by cross-ventilating it, so allowing air to go through here, we're generating kind of an increased heat exchanger. So we are kind of flushing away the heat at the roof itself, and we are protecting it. And so that the lower roof itself can be less, let's say, have less requirements for insulation and for protection of the heat itself. Yeah, so then energy production, I mean, a lot of sun means a lot of potential for active energy production, like solar, thermal and electrical. And then the wind topic, that wind, if it comes from certain directions, we might be interested in using it for space operation and conditioning. Yeah, so cross ventilation is something which we are appreciating. If you open up facades, we allow for porosity, but if a wind is warm, for example, or a wind is not intended to be useful, then you can just block it by allowing, let's say, it to flow aside the building. So we block here to the south, and we open up to east and west, for example. Yeah, and that is then, I mean, in combination, I think you've seen the example from Damascus, maybe in a former lecture, that we are really interested in using the air movement and using the sun as a heat source in order to naturally ventilate buildings, especially also in climates where we have a lot of sun and where the temperatures are more moderate and higher. So then solar exposure, we discussed about buildings. Ideally, if you have this kind of sun path, then buildings are having more, ideally more, let's say, from a certain perspective, more orientations to north and south, but less to east and west, in order, because these are very exposed to sun, east and west, with the sun angles, with the lower angles, and north and south is, we can protect them better from sun by architecture itself. Yeah. Then we can go on. We have this topic of ventilation, where we could deal with strategies in order to cross-ventilate. We could even orientate buildings, as we see in the middle, in order to generate a certain intended airflow. And that even goes along with the positioning in a master plan. You know, how far away do we position buildings? Yeah, and we know that at a certain depth, even if air flows over a building, it falls down into courtyard. Yeah, and we are really interested in, you know, improving ventilation of cities, of master plans, so that the air is not only just flowing over us on master plan, it's also going into the passages and corridors in order to generate a kind of natural ventilation effect there. There are some principles, you know, not to have, you know, these stacking of buildings after each other, but more maybe to really to position them sides, so that the air can also fall down, yeah, and between all buildings, and not only fall through here the main corridor, let's say. And this goes further. I mean, we can also look it up again, just with a little bit of explanation and examples. And for sure, what is relevant for us also is acoustics, in a way, so that if this impacts architecture, do we need to react with openings on it? You know, if we push for natural ventilation, is it possible, or do we need to think about cascading the airflow in a way so that we protect from noise, that we have a longer way for the air movement in order to really protect from noise and deal with it? Okay, I jump over this as time is running by, and I just wanted to show you this example with some architecture. It's a similar approach than what I've shown before for Aga Khan for the academy. Here we worked on, we had these brick elements, brick facades, we had window elements. It's a kind of a double layered solution. I show some floor plans also, where the intention was that this kind of porous facade here in front of the balcony is kind of the sun protection to west and east, but on the other hand, also allowing for airflow to it. There are some movable elements, devices, which are allowing for increased ventilation. And in this way, architecture could even react on the environment. I jump over the temperatures. It's for sure different to Kampala, but here in Kinshasa, it was a bit higher temperature. And but anyway, all the year sun, we have all the year potential for natural ventilation during certain times of the day. So it's really the interest also to bring in exterior air into the space. The sun path is quite similar, very high sun angles due to the closeness to the equator. And also radiation we have direct radiation and diffuse radiation almost the whole year, quite equally on a horizontal plane. Humidity is high as before in Kampala, and wind is mainly driven from west, so that we are really interested in how can we bring in air from the west side intendedly. The buildings is a residential building, was the study that we did here, and there was a lot of discussions about the amount of window openings, the amount of shading, and so on, and the distances to neighboring buildings, so that we, besides protecting from sun, we also need daylight, so that we have a good quality inside. And so the intention was for the south side to generate more openness, to just more have openings, overhangs as solution, but on the west side to have this porous brick facade, which is also protecting from the lower sun angles due to the depth of the structure itself. And you see here also the chimney, so the intent was really to naturally ventilate the building. And we discussed a lot about insulation and so on. And we needed to kind of, to generate the awareness from the client and from the architect to say, no, we should not overload the building. Let us rather keep it more simple. So it was a bit, the challenge was to get away from, our concern is we take solutions from Europe, which from Swiss, for example, or from Germany, we apply it one-to-one in your climate, for example, and this is a kind of a waste of material, it's a waste of energy and a waste of resources. And we have this challenge that we are rather need to convince that we don't need it, and it's a challenge in this way. So what we did here is we did a material study by, how can we maximize thermal mass effects, natural ventilation, passive cooling. And what you see here is an example. This was the base case where you have an insulated roof. We have these kind of the facades with a lower conductivity with these elephant bricks, so just hollow brick elements. And the question was, can we increase ventilation by increasing a chimney? Then the question was, can we change the bricks to less conductivity with more thermal mass? Can we then increase in the ceilings the mass by elephant bricks to integrate them? And also, can we, in the roof, maybe reduce the insulation by having also this double layer of roof, which protects the lower layer from the direct sun exposure. And then we talked about fans for natural ventilation in order to increase air movement, because we know in the worst what we can have is a day when you have no air movement, hot temperature and high humidity. But due to air movement, the effect of temperature and humidity are reduced, and we sense it even comfortable if it's humid and so on. And this is kind of even ASHRAE has these standards inside, so that you can also evaluate, what would be the impact if I increase air movement intendedly in order to improve comfort. So what you see here is then the effect. So we started from variance 0, where we do, let's say, not increased airflows, have less thermal mass, and we increased measures from thermal mass to air ventilation, and we bring down the temperature from 33 degrees Celsius, which we sense as the temperature, we bring it down to 28 degrees. And I think this is a really an amazing way of using passive measures. There's only architectural, let's say, influences in thermal mass, in openings, in the chimney, on the rooftop, plus the ceiling fans, which have so low energy consumption, and we are achieving at a high comfort level. But then, and even in bedrooms, we said, if bedrooms are only occupied during nighttime, the nighttime conditions outside are so nice, why don't you just open up facades? Don't forget about all the thermal mass, all the increased ventilation. If you just use it during nighttime, open up the facades, and then we can reach high comfort. So the summary was, we really worked a lot on the chimneys. We really appreciate with the architects that they took it so serious, and we gave them an understanding of opening areas, what the size of the chimney needs to be in order that the building is performing the way we want to have it. And this was quite nice. And then I have to admit, we talked in floor plans about, in the rooms, in the kitchen, in the restrooms, in the living room, how many openings and so on. I just jump over it. And then we ended up with some kind of requirements. The fan would be great, to have thermal mass would be great, the chimney and so on. And then the client came and said, but maybe our clients, consumers, would want to have air conditioning because air conditioning is a requirement. And we said, why the hell do you need air conditioning? And they said, it's just for principle. If you don't have an air conditioning, the building is not comfortable or it's not a high quality. And we said, it's so weird. This thinking is just nonsense. And that's really a big problem, that we just say, I need to have an air conditioning in order that it's comfortable. And then we try to convince the client, forget this, minimize it. If your consumer is in the way that they need air conditioning, it's just energy wasting. And we try to convince them in a way that they really minimize this by bringing in what happens if you integrate air conditioning. And I mean, honestly, before we had almost zero energy demand for cooling, zero. no energy. We reached the international comfort level for adaptive comfort. We reached it with our 28 degrees, and we are even far below it, the conventional definition of comfort. Yeah. And but then the client said, yeah, we want to have here 28 degrees with a fully air conditioning. So forget about the effect of air movement, forget about the effect of thermal mass. And then we showed them, if you do air conditioning, just by putting a machine in which cools the space down to 26 degrees or 28 degrees, you from no energy, you have 130 kilowatt hours per square meter and year of cooling demand, just by this kind of application of a system. And then, I mean, we left it open. I mean, if it, we said to them, it's nonsense from our side, but I mean, if you do it, and then we explained them, if you do this, then it makes sense to think about insulating the facade, because then you take all the kind of passive, more or less, performance of the facade you take out. We don't have any natural ventilation, more or less, because anyway, all the year it's conditioned inside. Then it makes even sense to think about insulation, because you reduce, by a better insulated facade, then under these boundary conditions, you even reduce 50 kilowatt hours per square meter a year of energy for cooling. So, and then that is so weird, then it comes back again that you can think about how to insulate your facade. And I think, like giving this, I just wanted to throw in this provocative examples. I think it's really important. Think about, you know, what is given by the boundary condition, what is the potential a building can give itself, but always keep in mind, if someone comes from the other end and says, anyway, I want to have an air conditioning device in any way, with all its, let's say, installation, ugly installation, and all its energy consumption, and they say, I just put in 26 degrees, then so weird it feels, but forget about the other stuff. It will be anyway an energy waste. And I hope this gives you some stuff to think about.
It's added material wastage of
yeah, exactly. Blood added material. So you know, you import maybe whatever Swiss insulation material, fly an airplane from one to the other side.
And the building doesn't disintegrate when its life is over.
Yeah, and I think if there are solutions, yeah, for sure you have to be site specific, look at the potentials, but just to give you an example, we are really happy to rethink it different. You know, what we are doing in these locations. And Aarti, or she put for you, we thought about making some workshop, but I think it's really difficult with the connection and so on. And so we put it here. Look at the CBE tool here on the lower level. You can do online or weather data analysis. I would really encourage you, do it for your next project, or just do it right after today, our lecture. Look at the climate, you know, look at what you get there, the details. There's so many potential where you could even evaluate annual, seasonal potentials of solar radiation, of temperature. And I hope that you got some of our presentation, and I hope that you are taking parts of it with you, and you know, take the boundary conditions of the climate as a serious factor in your climate, in your architecture, in the first step. Okay, so sorry, now we took a little bit time, so we needed the time to to go through everything, and we would now have a bit of time for questions.
Yes, thanks a lot, Christian and Aarti, for the great presentation. I will encourage the students to speak loud, unmute yourself, and ask all the questions you have in mind. Let's see.
Or if you write it, if you rather would like to write it into this chat, then also just feel free to. I jumped to a nicer picture again, so that we are
Or if nobody has questions, then any thoughts you would like to share, or anything that you did not understand, or something that you did understand and you liked, you can also share with us.
Oh, there's a chat. Wait a second. Hi,
It's me, it's me.
Yeah, I mean, anyway, I think if also questions come up afterwards, I think it's just good if you kind of collect it, maybe also for our next presenters.
Yeah.
So that we are getting kind of your questions after these presentations. And I know for sure it's a lot of stuff and like a lot of content now we went through, and it's I think it's really important, yeah, that it's not something you just do. You've heard it now once, and the expectation is not that you're directly now applying it. It's also a longer process for us to also to incorporate and to evaluate data. And what really helps is to look and to think about, okay, how to interpret and how to use the data, and it needs also a serious amount of time to really to work through it. I would like to encourage you in taking this stuff into your considerations. Okay, I mean, if there are no questions, I think we already took a little bit more time anyway. So Clara,
Yeah.
we are fine so far,
Yeah, I think, as you mentioned, Christian, if they have any question, they can just write us an email, and we can sort it out like that. Then I will thank you first, both of you, for the great lecture, and thanks a lot really for taking part in that. And the students that I see are not so many left in the meeting, but thanks for attending. And as always, you will receive the PDF of the lecture by today, as well as a survey that I really encourage you to take also today. Then, thanks a lot.
Thank you.
Thanks, everybody.
Bye.
Have a nice day.
Thank you.